So very pleased to welcome Professor Misha Kilmer. Misha's sort of local, just down the T, so down the New Green Line at Tufts University, where she's a William Walker Professor of Mathematics, and Misha's also a Deputy Director of SIAM down at Brown, which you can go to. It's a great place for conferences and so on and so forth. She's well known for a lot of work in numerical linear algebra, scientific computing, specifically the applications to inverse problems, tensor methods, and iterative methods. Misha's a SIAM Fellow. She's named a SIAM Fellow in 2019. Was section editor of SIAM Review for many years, and was a 2023 recipient of the Tufts Faculty Distinguished Scholar Award. And I think it's been a little while since Misha's come to MIT to give a talk, so really pleased to have you give the first talk of the series in this semester. So
thank you. Well, thank you very much for the invitation. And I get a new building and room and everything. So in thinking about what I wanted to talk to you about today, I figured this was maybe a group with a lot of diverse interests. And so the topic is
stop you 1 second, just flip your mic on.
Yeah. The topic is structured matrix approximation. We're going to do it with tensor decomposition, so I'll have to explain a little bit about what that is. And I have a number of applications. I just wanted to give a sense of just how broadly applicable this work is. And if you'll permit me just for a moment with my deputy director hat on for SIAM. SIAM runs a number of programs in mathematical sciences, and you should take a look and see what's coming up and register to attend or talk to me if you have any interest in putting together a program for either a semester program or for a workshop. So, all right. So the goal is we are assuming that we are starting with a block structured matrix A, and we want to find an approximation A hat that has also got appropriate structure, which I'll define in a moment, so that the Frobenius norm distance between A and A hat is small. The way this is going to work is that we are going to take our block structured matrix, map non-redundant blocks into a third order tensor. We will decompose our tensor with a suitable tensor decomposition, and we will map the tensor, the decomposition back into the form of a matrix. And what we will enjoy by doing this is uncovering some additional latent structure in the matrix. And the two types we'll be discussing are a block low rank structure or a Kronecker sum. Okay? And again, we will see a nice feature of this approach is that we're going to be able to preserve the block level structure through this technique. Towards the end of the talk, I'll give a sense of how this can be generalized to multi-level block structure as well. The nice features that make this thing work is that we need to define a matrix to tensor mapping that really only requires that we know the block level structure. And one nice feature is that structure is very general here. I'll give you some examples of that. Our method is completely agnostic to the algorithmic details of the tensor approximation. I'm going to talk about two specific tensor decomposition methods and show the results we get for using either of those two approaches. But another feature that I'm really pleased with is that the matrix approximation error really is identical to the error we get when we approximate the tensor. And not only does it have all these nice features, but we can preserve symmetry, symmetric positive semi-definiteness or symmetric positive definiteness if we need that. And this whole framework that I'm putting together actually subsumes or in some cases improves on known results. So I've mentioned the word tensor several times for this talk. A tensor, when I say tensor, I'm going to be talking mostly about third order tensors, basically three-way arrays of data. But towards the end of the talk, I'll be talking more about higher order tensors as well. And when you see a calligraphic letter like this, a bold calligraphic letter, it's going to stand for a tensor. So in terms of what can we do with these tensors we'll need to be able to slice them up in different ways. So if I have a third order tensor A, for example, I can slice it front to back into a collection of matrices that way. Of particular interest in today's talk is lateral slicing, so I can put matrices into a tensor by putting them in as lateral slices, for example. But if I wanted to get even a finer resolution here, I could look at the fibers of the tensor A, the tube fibers, the column fibers, the row fibers, and so forth. And so notationally, as I mentioned before, the calligraphic bold is going to be a tensor. Bold uppercase is a matrix, and otherwise I'm talking either about a vector or fiver or a scalar. Okay. Probably don't need this for this audience, but just to set the notation, I'm trying to tease out some Kronecker structure when I'm doing this approach. And so the Kronecker product between two matrices is what I have here. And you can see it's a natural block structure, right? The matrix B is repeated along all the block rows and block columns pre-multiplied by the entries in the matrix A. And the reason that we love Kronecker structure in scientific computing is it's really helpful in terms of computational and storage standpoints. For example, if I had A cron B and I wanted to multiply times x, I wouldn't do it that way. I would compute it as take the vector x, make it into a matrix capital X, left multiply with B, right multiply with A transpose, and then vectorize the result. And I would never explicitly form this matrix. I can store this matrix just knowing A and B. And of course, if we want to do things like inverting this matrix, if it's invertible, or factorizing it, we can do it using rules of Kronecker products on just the small dimensional blocks. Okay. So my co-author, Arvind, came up with this brilliant way of telling you my whole talk on one slide. So the idea is we have some block structured matrix. I'm going to take the non-redundant blocks out of this matrix, map it to a third order tensor, decompose that tensor in some way, and depending on what application I have, I'm going to use the decomposition to either take the tensor decomposition, map it back to the matrix, and come up with either a sum of Kronecker products representation for my approximation or a block structured factorization. And you can see by the color scheme how we keep the inherent structure down at in the approximations as well. And the way that I'm doing I've organized this talk is to basically interleave the applications with the discussion of how we get these two different types of approximations and what they can do for us. If you're interested in the paper, this appeared in 2022 in SciMax, and I've thrown in a couple of extra applications for kicks as well. All right, so I said that structure is very general when we're talking about here. So here are my two cartoons. The only structure that this matrix here on the left has is that it's block tridiagonal. That's it. So I can certainly look at taking the non-redundant blocks out of that block tridiagonal matrix and mapping it to a tensor. But the matrix on the right is certainly more highly structured. It looks like it's block toplets, and there's some symmetry there as well. So I want to be able to have a mapping that takes that into account. Okay. So I need to tell you a little bit about this matrix to tensor mapping because it's the key that makes the whole thing work. All right. So if I have my matrix and I label the blocks, the non-redundant blocks of that block matrix, A sub 1 through A sub p, that will give me a set script A of the non-redundant blocks of the matrix. Script E is a collection of very simple matrices here that tell me where in the matrix are these blocks located and how many times does that block appear. Okay, the how many times does it appear actually is a really important feature of this representation. So let me show some examples of this. Okay, but the idea is if I have the script A and the script E, then this notation struct with a subscript of E on A produces our matrix back again. Okay, so that's the basic idea. So if I know this collection of EKs and I know the eta Ks and the AKs, I can get back my original matrix. So a simple example, imagine just a block diagonal matrix, and this has distinct blocks along the main diagonal. So this is a block LM by LN matrix here, and the collection of E matrices is very simple, right? It's just the outer products of the canonical unit vectors. And in this case, because each block only appears one time, the eta Ks are 1. Okay, so that's a representation of this matrix. If I look at something that's got a little more structure, this is a block Toeplitz matrix, but it's not necessarily block symmetric. So then I need very simple Toeplitz matrices like these, just to have ones where A2, for example, occurs on that diagonal. And then I have to keep track of how many times each block occurs. Those are the scalars in this set E as well. So again, once I know script A, script E, I can put the thing back together again and get A. All right, so I mentioned this already, just to remind you, and I am using a MATLAB style notation in places. So when I'm slicing through things, for example, the jth lateral slice, it's colon J colon. All right. So the way this is going to work, I haven't told you how I get the tensor quite yet, is blocks of my matrix. I'm going to visualize them as lateral slices of a tensor. So the command that takes me from a matrix to its tensor equivalent is a twist command, and the squeeze command takes me back. The squeeze command actually is a real command in MATLAB. It's just that you have to type the whole word squeeze, and so I use SQ for an abbreviation. And you can see here now what I'm doing. I'm forming the tensor by taking the non-redundant blocks from my set script A and weighting them by their corresponding eta K, the number of times they appear in my matrix, and that will become the kth lateral slice of my tensor. Okay? So when I am done, I will have a tensor that is M by P, where P is the number of distinct blocks, by N tensor. And then notationally, we need a way to get back. So if you have a tensor script X and I want to take that X and make a matrix out of it, as long as I know what the underlying structure is, where to place things, and that's given to me by the script E, I can do that. So this mapping, this matrix to tensor mapping and tensor to matrix mappings, they're inverses of each other. So here's the algorithm. It looks kind of straightforward. Of course, the devil is in the details. But I'm going to determine these sets, script E and script A, from my matrix. I define my tensor, and I'll just call it X because the notation is quickly becoming a little cumbersome, right? So X is always the tensor that came from the matrix to tensor mapping. Then I will compute a tensor approximation to X, which I'm calling script T. And then I take script T. Implicitly, I map it back to get my matrix approximation A hat. So that's it, 4 steps. So next we need to answer which tensor approximation am I doing? And then how good is the matrix approximation? And then what structure does the matrix approximation have as a result of this process and the tensor decomposition? So I said I would mention 2 different tensor decompositions and the corresponding structure results for this. So the first of these is the CanDecomp parafac, or the CP decomposition. So usually, all right, that's the tensor rank. When people talk about tensor rank, it is the minimum number of these little rank 1 outer product thingies that it takes to reconstruct that tensor X. That's an NP-hard problem to come up with a tensor rank, so people don't do it. People pick, for some reason that they have a good feeling for what a good approximate rank should be, and then they solve an optimization problem in order to get the green vectors, the gray vectors, and the blue vectors, okay? So each one of those triples of vectors produces is a 3-way analog of an outer product, and is a rank 1 tensor. And so if you can approximate your tensor with this CP decomposition where you only need a very small number of these terms, then it's an implicitly compressed representation of that tensor, right? Because you're only having to store the factor matrices that have the green vectors, that's M by R, the gray matrix that has the horizontal components, that's P by R, and then C that holds the components into the board. And that's it for that whole big M by P by N tensor. Okay, so this implicitly compressed representation or approximation. Another well-known tensor approximation is called the Tucker decomposition. And for a 3rd-order tensor, the Tucker decomposition means you'll end up with an approximation that gives you a smaller dimensional core tensor. Here I've called it script G, and 3 factor matrices with different numbers of columns in the factor matrices potentially. I can always do this in polynomial time. I can always take a tensor and decompose it as in a Tucker 3 way, and I can do it by actually requiring orthogonality in those factor matrices. The basic way that this works is I take 3 different unfoldings of this tensor. So this is what's called the mode 1 unfolding of the tensor. So I take the frontal slices and I stack them next to each other. If I do a singular value decomposition of that matrix, that unfolded matrix there, and I keep the left singular matrix, that will, and possibly I truncate, that will become my AR1, for example. And then I do it 2 other ways. I do a mode 2 unfolding and a mode 3 unfolding. The details are not so important, but just know that it's basically involves 3 matrix-based SVDs to get the components that feature in here, right? So that's unlike the CP decomposition where the CP decomposition, the factor matrices don't have to have any orthogonality, okay? So this is when we do this is called the truncated higher order SVD. And we'll see both of these 2 tensor decompositions in the context of what I'm using them for will give us some very nice features that we can exploit. Okay. So just to summarize, X is derived from this matrix to tensor mapping that I introduced. And then I'm approximating X with T, and I'm either going to use a CP approximation or I'm going to use a Tucker approximation. In the case of the CP approximation, I have 1 parameter that defines how compressed it is. It's just R, right? It's the number of rank 1 terms. And in the Tucker approximation, I need 3 numbers. It tells me how many the compression for each one of the 3 matrix SVDs I had to do to get the truncated HOSVD. Okay, so this is really going to be interesting for me when the R term for the CP decomposition is smaller and hopefully much smaller than the smallest of the 3 dimensions. And in the case of Tucker, I want at least one of those 3 truncation indices to be smaller than the corresponding dimension for this to work out well. Okay, so here's the cool result, which is if I follow this procedure, then the matrix approximation error in the Frobenius norm is completely described in terms of the tensor Frobenius norm error, completely. So if I can control the tensor approximation, I know exactly what I'm getting with respect to the matrix approximation in the Frobenius norm, too. Okay. And okay, so what is this A hat? It's this tensor to matrix mapping that invokes that set of script E's that describe the underlying structure of the matrix. So formally, this is what it is. But we never explicitly assemble the tensor T that we get from the approximation. What I'll show you is that we will take the factorization terms, push it through this expression, and that's where we get our structured approximation. Okay. So the end result really is captured here, that whether I'm using the CP or the Tucker decomposition, I can show that my matrix A hat that I get from this technique is a sum of Kronecker products, that the number of terms in the Kronecker product is controlled by the truncation ranks for the tensor approximation, that the leftmost matrices in the Kronecker decomposition inherits the original structure at the block level, and possibly that depending on what I used to do this decomposition and some of the features of the problem, this DJ may even be low rank as well. So again, a picture to describe what I just said. If we have this, for example, block toplets type structure, I've now been able to approximate this block toplets matrix with a sum of Kronecker products where the CJs are single level toplets matrices and the DJs possibly are low rank. Okay. So let me show you where this is potentially useful. This is the sweet sparse collection of matrices. We just wanted to use this as a black box. So we went in and grabbed some different matrices, the individual blocks, different sized blocks, and we did a Tucker decomposition, and we only did compression on the second mode for that Tucker decomposition. So that's why there's only a cross with a 2 there. I didn't compress on all 3 modes, just a single mode. What that will give us is this A hat. Again, this was what I had on the last slide. And if, for example, these were block tridiagonal, for example, then the CJs would just be tridiagonal matrices as well. Okay, and if ignoring any structure that's within the blocks, but it does turn out that if there were structure in that blocks, it would be inherited by DJ as well. Okay, so these I think are really cool results. It basically is telling me that if I do, I compress on the second mode of the Tucker decomposition for these last few examples to 5 terms, I basically reconstructed the matrix exactly as a sum of 5 Kronecker products. And the compression is excellent, right? As opposed to treating this as typically you would take it and say, oh, it's a sparse matrix, and I'd use like compressed sparser format or something like that to deal with the matrix, I don't need to do that now. Now I have a representation that's far more convenient, okay, and faster to compute with. So, all right. The other type of structure that I can get from both using this procedure, if I don't need the sum of Kronecker product structure, is the following. So the whether I use an R-term CP decomposition or Tucker R1, R2, R3 decomposition, I can show that the tensor approximation mapped back to a matrix will give me this kind of nice structure. So this is an identity, Kronecker with a U. U has orthonormal columns. W has orthonormal columns. And the matrix here in the middle is a smaller version of, structured version of what I started with, okay? So this is really nice because there are lots and lots of applications where we want low rank approximations, and I'm going to show you some here in a minute. Okay. So surprisingly, maybe, this has an application in trying to identify the pieces, parts of the LTI discrete dynamical system that's expressed in this way. So what we're actually given are the entries of a matrix H. So we know these HK blocks, and really what I want to try and do is recover I need a low rank approximation to H of S, because if I have that, and it turns out I can recover this matrix little a up to similarity transform pretty accurately, and I need its eigenvalues. That's where I'm going with this. So the HS matrix, if you look at it, this is in fact block Hankel rather, right? It's constant along its anti-diagonals. And so we're going to use our approach to try and get an approximation to this thing. Okay. So remember when I told you that the truncated HOSVD came from unfolding 3 different ways, the tensor, right, and then truncating. So what I have in these 3 pictures are the singular values from each one of those 3 types of unfoldings. And what you can take away from that is that there are, at least definitely it's the second mode, but to a lesser extent in the other modes, right, the possibility for truncation, which translates into a compressed representation. So we use our technique. We end up with this matrix that I'm calling H tilde sub S. The U has orthonormal columns. The W has orthonormal columns. The matrix in the middle is still block Hankel, but now it's actually a lot smaller dimension. And we take that smaller dimensional piece in the middle, and we use an algorithm called the randomized ERA algorithm to estimate then the A matrix. And what we're ultimately looking for is the spectrum of A. So this is the actual spectrum from this particular problem. This is the eigenvalue realization algorithm output. That's the standard approach to doing this. And the black asterisks gives the result of our approach. And here I have written basically the floating point count. You see it depends on the truncation parameters and the total number of blocks in the matrix S. But we have a significant savings in the computation time versus the standard ERA algorithm, and much less storage that we're doing, right? So much faster runtime as well. So if we had done a much larger problem, I probably could have shown you something a little more dramatic in terms of the improvement in the computation time. Okay. All right, so application 3 is near and dear to my heart. I do a lot of work with inverse problems. So this is a particular problem that is known as a linear inverse problem. problem. So our model is that A here maps your unknown, maybe it's pixels in a digital image, plus some additive noise to the output B. So you're given A, you're given B, and you want to try and approximate X. Here, in these applications, the singular values tend to fall off really quickly. So you're certainly not going to solve, throw this into least squares solver because you'll just magnify the noise and you won't get anything back. But if A is not particularly well, if it's dense, even if it's structured, the algorithms that I would use to reconstruct this image would, be slow. So what I want to try and do is find an approximation A hat to A using our approach so that A has some kind of structure that I can then exploit in these algorithms for faster matrix vector products or what have you, okay? And it's perfectly okay to do this if you can say some nice other things about what features we capture in A hat. So what I, again, wanted to do is use this approach as a black box. So I took a spatially variant blur out of the Restore Tools toolbox, and I tried to approximate this with our matrix to tensor mapping and our using a truncated HOSVD for the tensor approximation. And what popped out was a surprise to me, actually, was that I got a very, very, very good approximation in just a single Kronecker product term. So here I just decided, well, that is really nice. I can do a lot of things with that, but I'm going to use it inside an iterative method where I can recover edges in a blurred image. So I took the matrix, the true matrix A, blurred an image, added noise, but used A hat in the reconstruction algorithm. So this is Tufts Jumbo. This problem was not very large. The spatially variant blur was a very small blurring problem. That's the blurred, noisy image in the middle, and that's Jumbo reconstructed with this approach using this approximation, which again, it's a complicated algorithm, but what it relies on are doing lots and lots of fast matrix vector products, and I was able to do that with this approach. Okay. So I said earlier we can adapt this to preserve symmetric positive semi-definiteness, and also to preserve semi-positive definiteness. I will just talk briefly about the case of semi-definite matrices because I have a nice example for that, and just let it go with saying if I do an extra step of pre-processing my block matrix, I can also preserve symmetric positive definiteness. And then I'll talk a little bit about generalizing to multiple levels of structure and what that means for our framework. Okay. So it turns out that if we look at the tensor that we get from our matrix to tensor mapping, if I started with a matrix that was symmetric positive semi-definite, then the blocks on the block diagonal will be symmetric, and those are put into the tensor. And then every submatrix on any subdiagonal will have to have its transpose also appearing as a lateral slice in the tensor. So the consequence of that is that when I go to do a Tucker decomposition or an HOSVD, the mode 1 and the mode 3 unfoldings have exactly the same range space. So I can use the same factor matrices on the first and the third modes to do the compression. And so G here, this is how I get the core, is basically unfolding along those molds, multiplying by U transpose from the left. That's how I get the core. And I need the core because the core basically gives me the pieces that I need for the reconstruction. Okay. So here is the example we had in mind. So this is a space-time covariance matrix. In this case, the blocks are structured like so. And here the lowercase x sub j refer to points in space, and the tj refer to points in time. We divide the world map into a 4-degree by 4-degree grid, and the x sub j are land masses. And what we want to try to do is approximate this space-time covariance matrix, which you note is block toplets, but C2 appears on the top and on the bottom and so forth. We want to preserve this. So if we take into account this symmetry, then it turns out we can get a very good approximation to this covariance matrix, at least to almost 4 digits in this trace metric. So we use the trace metric because it's easy to compute, and we don't have C explicitly. And the storage, I mean, the compression is phenomenal, right? We're storing r squared t plus n over r terms where r is the truncation in both the first and the third modes. So what we do with this approximation then is use it, for example, so we can draw now samples from the normal distribution mean 0 with this approximate covariance matrix here. And these are just some demonstrations of the samples using this approximate covariance matrix. Okay. All right, and finally, multiple levels. So this, if the notation wasn't bad enough earlier, it's about to get a little bit worse. Really, all I'm attempting to do is not give a quiz on this, but give you a sense of how this will generalize to higher level structure that we can take advantage of. This is part of the generality of this approach that I love is, again, the type of block structure that we're trying to capture on each different level can be different. So each level can have a different structure. It could be banded, it could be toplets, Hankel. It's fixed at the current level, but it can be different at different levels. So, for example, here is a multi-level example where the one structure that you can see from the left is that it's block toplets, but each one of those blocks then I'm saying is, well, let's assume it's block diagonal within each one of those blocks. So this has a level 2 structure to it. And so what I'm going to need here is a bigger tensor in order to be able to capture this information. So here's the ugly slide, but it looks very similar to the slide that we saw with the 2-level case, right? The kinds of things we need are the non-redundant blocks at each level, and we need to count how many times they occur at each level and keep track of that. And we need these indexing matrices for each level. And then we need to kind of extract away what we mean by twist and squeeze now, but we can still define a matrix to tensor mapping using just these features and dropping the appropriate things into slices of tensor. So if I have an L-level matrix, like this was a 3-level matrix, the example that I just showed, whoops, this is 3-level, capital L is 3, then I'm going to need a 5th order tensor. Okay. Oh, sorry, 2 and a 4th order tensor, yeah. And we can go back again, so this mapping is invertible, just as it was earlier. And good news, The CP and Tucker decompositions, although I just described them for you for third order, in fact, are well defined for tensors of order greater than 3. So all I need now is just a higher order version of CP or Tucker. And we can still prove that the error in the Frobenius norm between our matrix approximation and the original matrix is the same as the Frobenius norm error that we incur by approximating the tensor. So we can control it. And here's the implication of this, now that we have this whole framework together, right? I said I was originally ignoring the fact that whatever there might be structure in the blocks. I just was picking out non-redundant blocks and dropping them in the tensor. It turns out, for example, if your matrix was block toplets with toplets blocks, then it is a 2-level version of this. The higher order SVD drops down to one of the two of the dimensions collapse. So the higher order SVD becomes a matrix SVD. We truncate a matrix SVD, which is an optimal thing. And we will get back, for example, a sum of Kronecker products that's optimal in the Frobenius norm. So this was a result that was in a paper by Cam and Jim Nagy in SIMAX in 2000. They approached it in a completely different way, but now this framework subsumes that result. Likewise, they considered cases where the matrices were block toplets plus toplets plus Hankel with toplets plus Hankel blocks. This multi-level feature grabs all of that and is able to produce an optimal approximation in that case. But Jim and I also had earlier work where we were dealing with inverse problems that involved blurring kernels that were already themselves essentially tensors. And we kind of did a sum of Kronecker products approximation for that case as well. But this new model actually allows us to recover something even better than what we did in that paper. It's always good when you can give a talk and say, I have a new result that's better than my old result, right? Okay. So in conclusion, we have this new matrix approximation technique. It works for this block structured matrices. And this term structure is very general, as you saw with the sweet sparse, right? All I needed was really, block banded matrices. And it relies on this matrix to tensor mapping to remove the redundancies. We have this nice bound on the matrix approximation error in terms of the tensor approximation. And then what comes out are these tensor approximations that really allow us to exploit, computation speed, storage, parallelism, and so forth. And some of the structures are retained in the factorization, generalizes to multi-level. We can preserve symmetry, definiteness. And we have some other applications in mind. Mitchell Scott was a master's student of mine. He's now a PhD student at Emory. And Mitchell worked on applications to dense matrices that come out of fractional order PDEs. So, and with that, I am finished, and I'm happy to take questions.
Right, we have a good amount of time for questions.
Nice talk as always, Misha. So anytime I see a new way of representing a matrix, the 3 questions I'll always ask is \I SVD. Is there a general way? Would you do iterative, direct, or do we not know the best way?
So if I just want to solve a system, I can use this and do, it depends how many terms in your Kronecker sum, right? So if you have a Kronecker sum approximation, you can use an iterative method if you have more than one thing. If you have only one term, well, then it's easy to backslash, right? Yeah,
Same
yeah,
thing.
yeah. So 10 terms, and I'm envisioning using that as a surrogate for your original data structure in an iterative method to solve for the dominant eigenvalues or whatever. Yeah.
And whatever happens, happens, right? Because we don't know whether it's welcome, whether he's a preconditioner or not.
True, yeah, yeah. But I think you can use this technique to design preconditioners, so yeah.
Thanks for the talk. So maybe two quick questions. One is, it feels like that instead of collecting the blocks to be identical, you would just relax that to be within some epsilon ball, like cluster the blocks. Your error guarantees would probably go through the same, but
Yeah.
does the higher order SVD recover that for you at the expense of having to compute like a bigger HOSVD? Are they equivalent approaches?
So are you talking about making a, let's see, to first approximation, you're approximating blocks that aren't quite the same with blocks that are the same, and then proceeding through this? So I think you can control that. Yeah, the error in that approach. So the HOSVD sees only the tensor that you give it. So it's not going to see this first level of approximation that you did, right? So in fact, I've played around with matrices where the decay off the diagonal is so fast that I just said, I'm going to call it block diagonal, and I can get very good approximations with that. Yeah.
And then the second question is, in terms of automatically discovering this, let's say to make things simple, I have a 16 by 16 matrix.
Yeah.
I could think of that as 4 8 by 8 blocks or 16 2 by 2 blocks or whatever, right? Is there a quick way of iterating through to check the
I am
optimal
assuming
level
that I
of
know the structure a priori, right? Yeah. But I think that's an excellent question. I don't think there are too many people that have been thinking about that. Yeah.
So I guess my naive intuition is that somehow lifting to a tensor will tell you if these blocks sort of have common
Yes.
eigenspaces.
Yeah.
And does that now depend a lot? I mean, in Tucker, I suppose I could see it very much because you just literally line up the blocks in one particular ring before that. But when you go to CP, it's sort of less obvious. What's the intuition there?
Yeah, with the CP, because your factor matrices do not have to have linearly independent columns, let alone be orthogonal. If you use a CP, then the results for CP that involved factoring out a Kronecker thing that had orthonormal columns came from claiming that I could further reduce one of those factor matrices, right? That I could compress that down because of the dependence of the columns. But I don't know that a priori. That's one of the things with CP, right? You feed it into your optimization routine, you take back what you get, and then, yeah. So all the applications that we really did were using the higher order SVD, or Tucker. Yeah. So. Okay.
Thanks very much.